There we go. Record on his computer. So, did either of you get a chance to review what I posted on Friday?
Yep, I went through it.
Oh, awesome.
Sorry, I did not.
Okay, that's okay. You can catch up. Like this,
Yeah.
this. So I went through a whole bunch of different protection groups that we can use for this. So the point of this one was hopefully to have everyone here, and we could go through kind of applying them to a bunch of different situations. But seeing that it was really meant to be like super highly interactive, and seeing that there are two of you, and yeah, like the two most special, of course, but I think I might leave this lecture for another day and switch gears and cover something completely different that I wasn't going to cover. I just need to determine what that exactly is because I didn't think that I would actually need a backup plan.
Kirsten and I just finished writing Simon's midterm, so I don't know about her, but my brain kind of hurts.
Mine's been better, but
well, you know what? It wouldn't break my heart if. No, okay. You know what? I've already done this once. I'm not going to do it again. What I'm going to do is I'm going to just work through some stuff. You know, we'll get to where we get to, and we'll see that. So I'm going to cross this out. It's not that. It's we're going to talk about deoxy sugars and amino sugars. How was Simon's midterm?
It was all right.
yeah, could have been easier, could have been harder.
Yeah, could have been easier.
Okay, that's fair. I do promise my midterm is going to be funny assignments. So it's exactly as hard as the assignments are. So what I want to talk about is start with deoxy sugars. So what this normally means is any sugar that is missing an oxygen. An OH really. So normally it's one of the hydroxyl groups, C2, C3, C4, the C6 hydroxyl groups, not the oxygens associated with the anomeric position. I'm going to just turn my video on. So, and I'm going to minimize that because now it brings up my video. So the two big ones that you see a lot and that are really kind of relevant are fucose. So this is an important building block in a lot of bacteria. It's also really, really, really common in breast milk. Mammalian breast milk has an awful lot of fucose in it. I don't think that has anything to do with it being a deoxy. I have no idea. I don't know anything about breast milk. I have a collaborator in Mexico who had a PhD student visit us, and I was hoping to maybe send somebody down there like in the middle of winter when it's really, really miserable here so that they can visit Mexico. But this was not a good year for it. He works on these kinds of sugars, and he's interested in trying to see if they can better incorporate these fucoses and fucosyl glycosides, so sugars containing fucose, into formula, because hopefully you can get a better approximation of all the benefits that are in breast milk into a formula if you put the right sugars in it. That's the goal. So the other one that we're going to see a little bit, or you see a little bit of, is rhamnose. I don't know much about rhamnose. I know it shows up in broccoli, so we obviously eat it. But in these cases, these are both C6 deoxy sugars. But you also see quite a few C2 deoxy. These are all wiggly lines at the anomeric position. I'm just really wiggling it poorly. So this is 2-deoxyglucose. Now, I'm much less clear on the exact biological role of why these are particularly important. They do show up. They are relevant in immunology. They are relevant in sort of cell-to-cell signaling. And I'm sure there's people who have a pretty good idea of what they're doing and the role that is. But basically, you're not only can you play with, the 8 hexoses and their 8 enantiomers. You don't so much get the enantiomers in life, right? Life is pretty chiral. But you also have all the disaccharides you can possibly make, collecting those 8 different molecules in different orders. And then you complicate matters more by having these deoxy sugars, which give you a lot more flexibility and a lot more options. So, how do you go about making these? There are a bunch of ways to do this. The deoxy ones are pretty easy. You can make fucose on pretty large scale by taking galactose and getting a C6 iodide and treating that with AIBN and tributyl hydride. I don't think I think we walked through, yes, we did a mechanism like this when we were talking about making some C2, when we were doing the epoxides and the C2 epoxides and glycals. We talked about making halogens at C2 and the mechanism of AIBN tributyl hydride. And what this does is it basically, you abstract the halogen. You create the tin halogen bond, which is nice and strong, and you add a hydrogen to where the halogen was, and it's all radical. So if you need to revise that mechanism, it's back in our notes. So I'm going to leave that there. But if you want to think about how we get here, I think there's an interesting, not quite the whole thing I was going to do today, but we can talk a little bit about how we can possibly think about making this molecule. Actually, you know what? I'm going to leave that as an exercise. We'll talk about that next class, see if anyone has any ideas on how to do that. Because it'll be a good starting point for us next class when we're going through how to selectively protect and deprotect sugars. So what you want to think about here if you're going to approach this problem is you want to selectively protect all of the hydroxyl groups except for C6, which will be a C6OH. You could then swap out the OH for an iodide. We covered that with the Gehrig's iodinations earlier in the course. And then you could deprotect all the other OHs to open them up again. And so all you'd be left with would be that C6 iodide. But that's kind of a little awkward because now you got to introduce the halogen. It's a lot easier if you can just do it from an alcohol. So this is actually one of my favorite reactions. So let's say we had okay. So the reason I have an axial C4 and an axial C2 is completely arbitrary. It's because I ran out of space on the left-hand side there and there wasn't room to put it equatorial. But this is talose. That's the base sugar. It's axial C4 and axial C2. It's like if galactose and mannose got together and had a baby. And what we're going to do is we're going to take that, and what we want to do is we want to burn off this hydroxyl group. So if we want to go to this guy directly, what we're going to use is called a Barton-McCombie deoxygenation. Barton has the distinction of being one of the only chemists whose former trainees get together and celebrate his death by saying, "Thank God Barton is dead." Complete utter asshole, but he did discover this reaction, which doesn't save him from being a complete utter asshole. And I think it's important that we discuss when people are assholes, even when they do good chemistry, because we shouldn't forget that they're assholes. You shouldn't survive treating people like shit just because he did some good stuff. So what we're going to do is we're going to take the, I'm not going to worry about the rest of the sugar, we're just going to worry about the OH. And we're going to do 3 steps. Number 1, we're going to treat it with sodium hydride. Number 2, we're going to treat it with carbon disulfide, which is like carbon dioxide, but with sulfur. And number 3, we're going to treat it with methyl iodide. Number 4, we're going to heat it. Okay. So let's ignore everything else. Nothing else matters. We're just going to focus. It's all there. The phenyl groups and the benzols and everything. It's chilling. But let's just think about what we're going to do with these steps. So Susanna and Kirsten's brains are fried, and Samara has come online. Well, okay, Susanna's brain is fried. Kirsten's brain might not be fried, and Samara's online. So I don't know if anyone wants to guess what you do if you treat this with sodium hydride.
Reduction.
Sorry, reduction?
Hydrogen should go away, I guess.
What goes away?
Hydrogen from the hydrogen.
Yes, so deprotonation, not reduction.
Oh, okay. Okay, sorry.
There was actually a really famous paper published about 12 years ago where somebody said that they could use sodium hydride to reduce things. It turns out all their stuff was really contaminated with hydrogen gas, and it wasn't sodium hydride. It was like palladium things. And this keeps actually coming up because there was a paper published last month where somebody said, hey, look, we can do a palladium-free Suzuki coupling. I don't know if so. Suzuki couplings, you stick 2 arrow rings together, you use palladium. There's a halogen involved and a boron thing. And you need the metal because you need to do this transmetallation step and oxidative addition, all that shit. And one of the gold standards for industry has been, can we do this without using a metal? And this group said, yeah, we can. Look at this. And unlike a lot of groups that say that, they did really good due diligence on all the things to try and prove that there was no palladium anywhere. But then last week, somebody proved that there was like parts per trillion amounts of palladium in their catalyst. And if you make the catalyst without using palladium and you don't have that parts per trillion of palladium, the reaction doesn't work. So you can use really, really small amounts of palladium and it gets things to go. So somebody did show that sodium hydride did reductions, but it wasn't sodium hydride. It was a hydrogen gas produced and then the trace palladium that was present from something else. Trace palladium, which just tells me that we use way too much palladium in all of our chemistry if you can use trace palladium and get things to go. Like if you can't see it still works, then why are we dropping in like milligram quantities?
So why does this start even coming in the undergrad courses? The removal of hydrogen is reduction, and maybe it's all about the
removal of a hydrogen atom, H dot, is reduction.
Okay.
But we aren't removing H dot, we're removing H plus.
That's a deprotonation. Makes sense. Thank you.
So you're not, yeah.
It's a terminological issue. I must correct it. Thanks, Ron.
No worries. Or rather, sort of a gain of hydrogen is normally a reduction. Loss of hydrogen is normally oxidation. So what we're going to do here is we add CS2. Any guess as to what happens?
it's like it's me whose brain is fire, burned up.
Yeah. Well, you have the excuse of it being really late at night. So you all have good excuses.
Yeah.
Does the negative charge on the oxygen just attack the carbon?
Yes. So we're making something kind of at the carbonate oxidation state. So we have a carbon with 4 bonds to a heteroatom. Like if those are not sulfurs and they were oxygens, it would be a carbonate. I have no fucking clue what this is called. Like a thiocarb. This is called a xanthate. I do know what this is called. This is called a xanthate. You don't need to know that. It is completely irrelevant. It's just I'm really proud of myself because I actually know what a functional group's called, and I really suck at this, and so I think it's not very important because I suck at it. So you make a xanthate, then you treat that with methyl iodide. Kirsten's the only one who hasn't popped in with a mechanism yet. I think you can get this one. Which I'm sure you can get this one.
Well, it's an electrophile, right? So, it. Yeah, I guess the sulfur would attack it.
Sweet. Absolutely. Okay, so this is the true xanthate. That's probably like a xanthonium or a xanthosulfonium. I have no idea what the hell that thingy is called, but this is the true xanthate there. Okay, that's weird. And there's likely a reason you haven't seen many xanthates around, because they're not really very stable molecules. So what happens with the xanthate is you've got a few options on how to burn this thing off. You can either heat it, as I've drawn here, or which works well, with the caveat being that if you do it wrong, you destroy the rest of your molecule. So we tend to go with a much gentler conditions, and that's AIBN and tributyl tin hydride, which is going to be a reduction because we are going to add hydrogen atom to it. So what happens here is we generate our AIBN radical. I'm going to actually flip to a new page and give myself lots and lots of space. That's a tin. So I'm just going to give myself some space. I'm just going to draw out the xanthate. Okay, so let's keep our eyes on the prize. And that's getting rid of the xanthate. So we generate our AIBN radical. I was trying to write from, I think my brain's fried and I've got no real good reason for it. So what we can do here is we add the radical to something. It's a little weird. So we're going to take this. This will react with the weakest thing in there. Which is surprisingly a tin hydrogen radical. You could also actually do the next step. I'd be okay with either adding it to the tin or to what we're going to do next. I don't think it really matters. And that's now that you have this xanthate thing, which just seems to have way too many bonds to sulfur for anyone's comfort. These sulfur's behaving like a normal atom with only making oxygen level bonds. So what we're going to take advantage of here is that sulfur is a very soft atom, like it's big, and it actually is quite stanophilic. It likes its tin a lot more than oxygen does. So a sulfur tin bond is a pretty good bond to make. And so that's what we're going to generate. And that's, again, I really want to draw sulfurs. That's because the size is kind of similar. I'm just going to make a note of that. Both big plus soft love each other. So we make a sulfur tin bond. What that means is we generate a radical there. And what that leaves us with is now we want to stabilize that radical, and we've got some options. Now the thing to remember is we can go backwards and we can lose the tin that we just got, which is okay. That's maybe the most likely thing to happen, is to go completely backwards. Or we can make a sulfur carbon double bond and lose a methyl radical. And if you remember back to first year chemistry, methyl radicals suck. You want substitution on your radicals. You want your radicals to have lots of, as many bonds as they possibly can. So tertiary radicals are better. Also, sulfur carbon double bonds aren't particularly strong. They're not awful, but they're not particularly strong. I have another option. I can make an oxygen carbon double bond and generate a secondary carbon radical. Because remember, this is part of the whole sugar thing. That's pretty good. Now I have a secondary radical. It's a lot better than a methyl. And instead of a sulfur carbon double bond, I get an oxygen carbon double bond, which is a lot more stable. So everything is kind of saying, you know what, maybe radical, you really want to do this. I'm just going to keep the hydrogen that was here still here. There's something beautiful about that thing on the right. It's aesthetically pleasing. And then I have a carbon radical, not particularly happy, not particularly stable. Luckily, I've got lots of tributyl tin hydride available. And oh look, we're done. So we have burnt off that oxygen. So overall, what do we do? Over those two steps, I'm just going to slide back a slide. We took this guy. We did sodium hydride, CS2, methyl iodide, 1, 2, 3, all in one pot. You literally add them one after the other. It's a lot of fun to do this reaction because you feel like an alchemist where you're just like mixing the chemicals together and it's bubbling because it's refluxing, so it's bubbling liquid. And then you do need to isolate because it all fucks up your AIBN. But then you take your AIBN, tributyl tin hydride. And you go all the way down to, well, hydrogen. So it looks like a lot of reagents. Mechanistically, it's a lot of steps, but it's actually very, very simple to do. and you directly convert an OH to a hydrogen. This works on, it's not just a sugar thing, it's like a general reaction thing if you want to get rid of an OH. Barton-McCombie is actually really, really tolerant of a lot of other functional groups because that xanthate is so reactive to AIBN and tributyl hydride that you can do it at lower temperatures than almost any other thing that you can reduce. You can remove xanthates in the presence of halogens. And we just saw that you can use those same reagents, tributyl hydride and AIBN, to remove a halogen, but you'll remove the xanthate first. It's just a lot more reactive, which is very helpful. So I misspoke with the heat. My brain is a little weird. If you have heat, you get something else happening with the xanthates. Let's just think about what can happen. So what I'm going to do here is I'm going to put the xanthate on the C6. And it's a xanthate. And I'm going to give myself more space. So if you take a xanthate and you heat it, this never worked for me, but I'm told it works great. If you heat it to 150 degrees Celsius, what you can think about is the fact that, again, we're coming back to this idea that all those bonds, this carbon-sulfur bonds aren't great. We'd really like to trade a carbon-sulfur double bond for a carbon-oxygen double bond. And so if we're thinking about that, whenever you're seeing something like this, it's never a bad idea to start counting atoms. 1, 2, 3, 4, 5, 6. And there's nothing nature loves more than a 6-membered ring. So you heat this enough. You get out your orange marker. I'm going to use the electrons in the bond. If they grab that hydrogen bond is going to move up here to make a double bond. And we can break the carbon-oxygen bond to make a new carbon-oxygen double bond. We can number the arrows if that helps you. Maybe it doesn't. And we end up with kind of like a double deoxy sugar. That's actually what it is, with the double bond up there. Now I want to make sure we know about that because we're going to come back to sugars with double bonds up there. This is kind of like a, well, it's an exoglycal. Because what we're doing is we're losing an H and an O. It's exactly what we've been seeing with some of the glycals. It's an exoglycal. So these xanthates allow us to do that. Now, if you have it at the C2, you'll eliminate to make a glycal. So, what time is it? 4:30. And notice I'm really focusing on C2 and C6. That's where those things really show up in nature, is on 2 and 6 for these deoxy. There's nothing stopping you doing this on 3 or 4. You can make some interesting molecules that way, but they don't exist in nature, which is fine. I'm all behind making things that don't exist in nature. You can get really interesting activity that way. But you're often, if you're targeting an enzyme, you're not as useful because you're not mimicking something that's present. And so you normally would have an OH there that's interacting with something. So an ASA sugar just means nitrogen present. And again, the two dominant ASA sugars, amino sugars. Aza means it's in the ring. We'll come back to them. Aza sugars. I don't really care too much about those right now. The two dominant ones you see, and actually if you go to the Costco, you can get glucosamine. So if you've ever seen glucosamine, you need it. Notice it doesn't tell you where the amine is. It just says glucosamine, and you're supposed to know it's a C2 amino. This still bothers me. I still want to call this like glucose 2 amino. It's actually 2 amino 2 deoxy glucose is the official name. So you need to say the oxygen is gone and the amine is added, because glucose itself has an oxygen there. So you need to say that the oxygen is gone, the amine is added. So you see that one, and then you see some galactosamine, which is really, really important for all sorts of things in your body. And Sigma Aldrich sells it really, really expensively because I try and buy it regularly and check the prices. And there was like one period back in like 2013 when they were selling it really cheap for some reason, but I didn't have a lab yet. But I'm always hoping that 2013 will come back around again. I'll buy like 10 kilos of this stuff and be good for my career. Otherwise, we make it. But these are the two main amino sugars that you see are these C2 nitrogens. These are the ones that exist in nature. I don't know why. I have absolutely no insight into that. Now, Nate, if you spend a lot of time doing any kind of natural product stuff, or even like biochemistry, you don't see a lot of free amines. Nature really abhors free amines. It really likes protecting them. So what these things often exist as is they're N-acetyl things. So although we've been talking a lot about acetate protecting groups, nature does not use acetate protecting groups. It doesn't need them. It does protect these nitrogens as acetates. So N-acetyl, I'll just draw one right now. Glucosamine is basically nature throwing a protecting group on a nitrogen, so it doesn't do any chemistry like nucleophilic attack or breaking down some thiols or, I don't know, whatever nitrogens do. So you have a NAC group on there. I really love this because it is nature using a protecting group, and that's kind of fun. So these show up a lot. I'm really, really interested in these personally because we're going to talk a little bit more about this. I'm just going to actually throw in a little bit of biology right now. So one thing I'm really interested in are, and this is the wonderful thing about senior classes, you start talking about whatever you're interested in talking about. So the tumor-associated carbohydrate antigens, or TACAs. Everyone's brain's fried, so let's do some biology because it's easier than chemistry. So what these are is, so on your cells, I know we were talking briefly about this, but you've got these proteins, and they're the mucosal proteins. So you got, I don't know, there's like 19 of them. And what they are is they're tandem repeating units of about 6 to 19 amino acids long, depending on which one it is. And they've got a lot of sugars on them. And so the way they do that is they put a serine in here. So let's just zoom in. We zoomed in. It's an amino acid, which we're going to talk about starting in a few lectures. So it's a serine, and that serine is attached to a sugar. And that sugar is almost always a galactose amide. This thing here I've just drawn here is called the TN antigen. The T stands for Thompson, who is a guy, but he's German, so he spells it weird. And the N stands for Nouveau, because this one was found out by a bunch of French people who didn't find the Thompson antigen. They found the new Thompson antigen, so they called it the Thompson Nouveau antigen. And this was all in the 1800s. Anyways, I'm going to delete that arrow because it's kind of confusing. I'm also, sorry, I have a really bad habit, and I'm going to try and correct it, but I'll forgive you guys if you do it too. When I draw N-acetamides, I should put in the H that's also on a nitrogen. I always forget to do it. I have it implied there. I didn't put negative charge. I'll be insane. So there's got to be an H on it. So if you do that, that's fine too, because I am going to do it, I promise, and I'm sorry, but I mean to have an H on those nitrogens. And I did it down here on this amide as well, because of course I did. So this is actually a cancer marker, and it's only found on cancers, and it's found on greater than 90% of all carcinomas. Regardless of organ. So this is fascinating because when I think about cancer, I think of cancer as being, I don't know, I'm actually curious. Any of you guys have like a running definition of what cancer is in your mind? Like how you define cancer?
Cellular metabolism going so bonkers that it cannot stop, replicating itself.
I really like the use of bonkers in a working definition. That's awesome. So cellular metabolism going so bonkers that you can't stop replicating yourself. I'll go with that. I think that's like my thinking process in my head is it's the misregulation of cell division to the point that it will lead to death of the host, because you can have there are diseases that involve misregulation of cell division that don't lead to death, like there are benign tumors that for whatever reason it seems to be misregulated but slightly controlled, um, or endometriosis, which is like the growth of uterine lining tissue outside of the uterus, and that can grow everywhere. That can grow in your brain. That can grow in your lungs. It can grow in your heart. Um, I'm lucky I'm male, so I'm not going to have any uterine tissue growing anywhere. But that tissue already grows quite rapidly because it's recycling every month, right? So you're already fast growing tissue. But that also doesn't lead to death. It can lead to all sorts of complications, but not death. And so cancer to me will evolve to lead to death, but it is misregulated cell growth. But that's all it's got in common, right? Like there's what we're basically talking about is a syndrome rather than an actual disease state. So there's, a lot of cancers don't have a lot in common. So the fact that 90% of carcinomas have this one marker on them is just ridiculous. Like that's insane, because there's all sorts of ways you can lead to misdirected cancer growth or cell growth. So no one's exactly sure why this is showing up in all these carcinomas. And so carcinomas are any cancer of any lining tissue, any surface tissue. And they're some of the more common cancers, and that's because those cells are kind of poorly regulated anyways. They're turning over very quickly. Like your skin cells, your lining cells on your liver, your lining cells in your lungs, those are turning over a whole lot faster than like your neurons or your muscle cells. So you tend to get cancers of these cells that grow quickly anyways. But there seems, I don't know, like I've got lots of ideas on this, but it's pure speculation. My thinking of this is that these markers must have something to do with the cancer's ability to evade the immune system. Because the one thing I'd like to add to that definition that Samra gave and that I gave is that cancer is when cells' metabolism go bonkers and they evade the immune response to kill them. Because we are constantly having cells getting misregulated and going bonkers and outgrowing, but our immune system comes in and mops them up and kills them off, and we never notice it because it never gets to a cancer tumor or anything. So cancers by definition are cells that have already evaded your immune system. And one thing that I'm always thinking about is if the TN antigen is really helping, and these other related TACAs, there's like 5 of them, are helping your cells evade the immune system. Anyways, sidebar. Normally on your healthy mucosal proteins, you've got this TN antigen, but it's not alone. It's decorated. So you'll have more, what'll happen there is you'll have your GalNAc, and it's literally GalNAc is how that's referred to, but it will be branched. It'll have things attached to it. And, you can look at these diagrams, and the carbohydrate biochemists have these different shapes for different sugars and different colors. And it's really, really colorful. Look at this. But this is kind of how they code different sugars. So you have this GalNAc core attached to the peptide, but then you have these other sugars kind of building off of it. And there's a lot of variance in there, and that can lead to the signaling that happens between cells. These mucosal membrane cells, the reason they have these sugars on them is they're talking to the other cells and they're signaling, and we do have no clue what they're saying. But if you look at cells under stress or cells in different organs, they'll have different sugars on these muc proteins. These are abbreviated muc. So there's muc 1 through 19 or so. But there's probably now more than 19 because, I don't know, my numbers are out of date and people are constantly finding new proteins. It doesn't really matter. Like this, what the sugar is seems to matter more than what the protein is. So what's happening in these cancer cells is, like, a sugar is not an enzyme. You can't mutate the sugar. It's GalNAc. What you're doing is you're mutating the proteins that add more sugars to it to make these kinds of systems. So we're kind of actually getting a mutation by deletion here. Like we lose function of the glycosyltransferases that add more sugars to this. And we end up with this bare, naked TN antigen on the surface. And this is associated with cancer, might help the cell evade the immune system, might help the cell. There's a lot of talk about, well, this helps the cells invade new tissue, this helps the cells metastasize. I'm not as convinced by that because the argument there is always, well, sugars are sticky and that helps with that, which involves an awful lot of hand waving in my mind, because in a healthy cell that's covered in sugars, and those are really sticky. And then sometimes people say, well, the sugar is sticky and it helps with that, and then the sugar is not as sticky as it normally is, and so it's less likely to be stuck, so it can kind of float off and metastasize and spread. Okay, but you have so many of these things coating the damn thing. It's like cells are pretty sticky. Like, you don't think it really matters if there's a single sugar or not. So I think at this point it's just random freaking guesses over why these are involved in that, but they're doing something, obviously. And the whole thing that makes it more confusing is the immune system just doesn't really see sugars. So why does this matter at all? And I kind of give up. I think I was talking about why these were important. I really don't know why I went off on this tangent. I just really like TACAs. We do research on them in the group, and it gets me excited. So if you do want to read more about TACAs, we actually have a review article that came out of this class a few years ago on TACAs. I guess 4 years ago now. But where I want to go with this is, how do you make these freaking nitrogen sugars, because they are really stupid expensive. And so if we want to make a nitrogen sugar, effectively what we want to do is we want to take something cheap like glucose, and through a pure series of reasonable synthetic steps, we want to introduce a nitrogen. Now, there's a bunch of ways you can do this. So one of the best ways to do this is actually something we've seen. So you take this and you take this to a glycal. We've seen how to do that. You would acetylate the whole sugar. And if you haven't reviewed the lectures that are online, you should go and look at that, because we talked about that just the week before the break. We talked about getting the alpha or the beta acetate depending on which conditions you use for the acetylation. So let's stick some acetates on here. And then we can do what's called an azidonitration. This was game breaking when they found out about this. Azidonitration. Set the sugar world on fire about 30 years ago. And like so many other things in the sugar world, the organic chemist world was aware of this about 20 years before that. It just took its sweet ass time to get over to the sugar people because we aren't very good at bringing in new knowledge. I note with interest that my postdoctoral advisor finished his PhD in 1978. And he used to call all the palladium coupling chemistry newfangled bullshit because it all happened after his PhD. And I thought, well, I was working with this guy in like 2012, which is, 32 years after his PhD. And I went, well, this stuff's really established. This was invented like 30 years ago in the early 80s. But it was after his PhD, so he didn't really trust it. He didn't really believe in it and stuff. So we didn't use it much in his lab. And what I'm noticing now is it's happening to me too. I'm not keeping up with things as quickly. And so this new kind of chemistry that's really emerging, there's a lot of new photo redox and gold catalysis and stuff. And most of it's happened after my PhD. And I didn't learn it during my undergraduate studies and during my early PhD courses. So I think of it as this newfangled bullshit. It works really well. Anyway, so for a lot of people,
Focus
it's the same thing.
chemistry.
Sorry?
The hocus pocus.
Yeah, exactly, right? I actually still don't understand gold chemistry. I keep telling myself I need to sit down and do it, and I kind of then understand it, and then I forget it. So I guess this happens to all of us. We become what we dread at some point. So what we're going to do is we're going to take advantage of the fact. So anyway, sugar chemists are very much like that. So innovations in a lot of the rest of synthetic chemistry take forever to get in here. It's only been in the last 5-10 years that we're starting to see a lot of that palladium stuff that was developed in the 1980s move into sugar chemistry. So I'm actually really hoping to actually grab some of this gold stuff and really run with it with the sugars because we can get in there early. So I really want to understand that because I got about 15 years before anyone else catches up at this rate. Anyways, so cerium. That is cerium 4+. If you count, you got cerium, you've got 2 ammoniums, and you got 6 nitrates, and you can do the math. So that's cerium 4+. Big, soft metal, loves chelating to double bonds, and that's what it's going to do. Now, what's going to happen here is we can think of this as the azide. It's also going to kind of associate itself with that ring oxygen, huge metal, which then means that the azide is going to come in at the C2 position, break that bond. Now, I don't know if cerium is actually 4+. It probably still has some ligands on it. I'm sure it's got some ligands on it. So let's say one of those ligands is still a nitrate. There we go. There's NO3. What am I drawing wrong there? No, that's right. Yep, it's going to be negative over there. So what we have here is we have cerium attached to the carbon, just because we broke the bond. It's no longer, I guess, cerium 4 now. I guess it's got a carbon bond, probably actually cerium 2 at this particular stage. No, it's still cerium 4. We're about to go to cerium 2. But we're still cerium 4. And so what we can imagine here is basically a reductive elimination. Okay, I don't know how many of you guys have seen. How many of you are familiar with palladium chemistry, like Suzuki couplings, oxidative addition, transmetallation, reductive elimination?
I am. I studied that in my
Good, you
undergrad
are.
courses.
That makes sense. Kirsten?
Yeah, Susanna and I are currently learning
Good.
it in Simon's class. Yeah.
Okay, awesome. So that's exactly what's happening here. So it's not palladium, it's cerium, but it's the same principle. So like an organic chemist, I need to draw arrows, otherwise I get really nervous. So I'm going to use, I like oxygen as the nucleophile, so I'm going to use the oxygen atoms. No, I actually can't do that. I want to use the oxygen atoms, but I'm not allowed to. I'm going to use the carbon cerium bond to make the new bond with oxygen with retention of configuration, which is what you get with reductive elimination. And the electrons in the cerium oxygen bond will just go onto the cerium. So we get the azide and we get a nitrate at the anomer position. That nitrate is about as stable as you imagine it is. So if you shake this with some water by accident, you get a bit of acid. Otherwise, you get partial deprotection of the azide. It's really irritating. You get the OH in the azide. Nitrate. You get the OH in the azide. And of course, that's a mixture of anomers because it's an OH and it's got meter rotation and free rotation and all that stuff. So what we've done here is we've taken the OH, we've gone to the glycal, we've taken a glycal, and in one step we're able to install the azide, and we install it with the glucose conformation. You don't get the mannose, you don't get this axial. The cerium sits on the top face because this is the more stable boat, and it needs to interact with the oxygen. And if it's on the bottom face, it can't do that as well. It sits away from it. So you get this form. That's pretty cool. Now, the really nice thing about azides is they're nitrogen without being nitrogen. So if you've ever worked with amines, they're pains in the asses. Like they really are. They're an awful, awful functional group. Because they're really nucleophilic and they're really basic, so they're always protonating themselves. They're always sticking to silica. They're always dissolving in water. They're just irritating. And if you protect them as an amide, that sounds nice, but amides are base sensitive. Amides tend to stick to stuff. Amides tend to react. They're frustrating. Azides, like except for the whole exploding thing, are really, really stable. Like they don't do anything. They're inert. So they just kind of sit there. So the nice thing about having the azide is that it's a way to have that nitrogen installed without having to worry about it doing chemistry. Because nothing's going to happen until you reduce that azide to an amine. It's just going to sit there being an azide. So we have some options. If you want to take this down to the amine, you can use a Staudinger reduction. You can, I can't, because they don't work for me. But there's nothing wrong with it on paper. You can use hydrogen on palladium, if you like that. I guess that goes, I'm just going to call this product. That goes to the amine as well. This all goes to the same thing. One of the really nice, gentle ones that really works very well is thioacetic acid. So it's like acetic acid. It's like ACOH, but it's ACSH. I'll just draw it like that. It makes a little bit more sense. And that reduces the amine and also makes the acetate all in one step. And that's because you actually basically have the nitrogen displace an SH2 group. It stinks. You can actually smell the SH2 being escaped. But it's very, very clean reaction. It's kind of cool. I'm going to draw closer to the arrow so it is clear what the fuck I'm talking about. So we have these different ways. And of course, once you make the amine, you can always acetylate it. And normally you end up acetylating it because the free amine is not all that common in nature. The acetate is, or the acetamide is. So that's one way to make an amide. There are other ways to do this, right? What we saw when we had the galactiles and we were installing different things at the anomeric position is, if you remember, we could easily get something like this. So, of course, that is an iodide. And the wonderful thing about azides is that they're wonderful nucleophiles. Really crappy bases, really good nucleophiles. So, unsurprisingly, this just does an SN2 on the halogen. So you can introduce the azides using SN2s. Maybe a less common way of doing this too, although it does have its uses, is, let's say you had an OH over here. You can oxidize that. So take your favorite oxidation conditions, but you need to be a little bit careful you don't oxidize this guy. So if you haven't, I'm not sure we covered this in this class. If we didn't, then you should still know this one. You can do a Swern oxidation. Very gentle. And you will oxidize that up to the carbonyl. You could also there's a bunch of different reagents you could use. I'd be happy with a lot of them. I'm not going to go through all of them. But I think Swern is something you should be aware of. The other one that you might want to know for this would be Des Martin. I don't think, again, the assignments are where the questions are coming from for the exam. So there's no surprise. I'm not sort of hinting at anything here. I just think there is per iodinate. I think that these are just reactions that, you should be familiar with, or the existence thereof, even if you don't have the mechanism at the tips of your fingertips. But these are very selective oxidations of alcohol up to the ketone oxidation state or the aldehyde oxidation state without over-oxidation. Anyways, so we have this guy. What we can do then is basically a reductive amination. So you can treat that with a nice amine. And if you're there for my last course, or you pay attention at the very end when I kind of wandered around a bit, I finally settled on the idea that I wanted to talk about the Paramethoxy benzoyl ethers. And I left off the paranitros because they're pretty similar and we just didn't need them. But if I take Paramethoxy benzylamine, a little bit of acid, and sodium cyanoborohydride. And if you remember, sodium cyanoborohydride is like sodium borohydride, except it only reduces imines. It's not going to touch a ketone or an aldehyde. It's not reactive enough. It needs a carbon-nitrogen double bond. Of course, that is exactly what I'm going to get with these guys. So we think about that, and we're going, okay, I'm going to make my carbon-nitrogen double bond. And there's a reason I've picked this particular amine. It's probably the best one out there for doing this. So we make that. That's in brackets because if there's sodium cyanoborohydride, it's not sticking around very long. I am going to add a hydrogen to that. I am going to reduce it. And I'm going to reduce it from the axial position, because whenever you have a small nucleophile, a small hydrogen nucleophile, it almost always prefers to attack axial. And that's because you're going through a more chair-like transition state when you do that. And so I'm just going to draw this in a different color. So this works great if I want glucose. Notice I start with galactose. I'm going to a glucose form. If I wanted the galactose form, I can't do this. I have to do kind of some sort of inversion chemistry. Anyways. So what we've just done there is we've now gone, if you're keeping track, and I guess there's some water. Well, there's acid. There's some water. And that's going to be the source of the hydrogen on the nitrogen. It's going to be like a little bit of water, a little bit of acid, work up, whatever. Normally you do this in a little bit of water or methanol. So what we've done here is we've taken an alcohol, we oxidized up to the aldehyde, we did an imine, and then we did a reduction. So it's oxidation followed by reduction amination to make the carbon-nitrogen bond. And now we can use DDQ, which we covered in the last lecture, to reduce this bond here. I'm not going to go through the mechanism of that because it's exactly what we just covered, except with oxygen, nitrogen instead of oxygen, so it's actually even easier. And we burned off that protecting group. So we kind of introduced the nitrogen with a protecting group. And the reason we did that is this chemistry really sucks with ammonia. Like, it would be nice if you just, like, why bother doing that? Just don't have an alkyl group there in the first place. And ammonia as a gas is a real pain in the ass to work with. It's actually really problematic to do this kind of chemistry with it. So it's a lot easier with something on there and then removing it afterwards. And the nice thing about the DDQ is it's very, very selective. You can have any kind of thing on that nitrogen if you can get rid of it. It's just a lot of other conditions are going to be a lot harsher to break a carbon-nitrogen bond. This is about as gentle as you can get and selective. So we found a way here to introduce nitrogen as well. So what we see here is we've got three different ways we've seen to introduce a nitrogen. We've seen, if we want it at C2, we have this azidonitration strategy that works quite well. If we want it anywhere, we can always put in a leaving group, like an iodide or a triflate, and do an SN2 reaction. And if we want it to end up equatorial, we can always oxidize the alcohol and then reductively aminate, and that will deliver the hydrogen axial, so we will get our nitrogen equatorial. So we have those options. I think I want to talk about a lot of this other stuff when we have everybody around. I'm going to introduce, we've got, what do we have? Got 10, 15 minutes left. Screw it. I'm going to just talk really briefly about azo sugars. So azo sugars are when you replace the ring nitrogen with an alcohol or an oxygen, the ring oxygen with a nitrogen. Oof. So how do you do that?
How do we name them? Must be some
Yeah.
twisted.
So
Yeah.
So I gave this there. So this would be alpha D azoglucose.
Oh.
But if you wanted to get really particular, because this is acceptable, everyone will know what you mean by this, but that's not really all that good. So again, it's alpha because anamerically that's down. I guess glucoside. I didn't say what the R is. We could call it alpha D 5-deoxy 5-amino glucose. That's effectively what that is, because what we've done is we've taken the C5 oxygen, which is the ring oxygen, and we've swapped it out for nitrogen. And that is literally how you make them. Is what we need to do is we need to swap out that C5 oxygen for a nitrogen. So let's think about what that looks like. So let's say you have a sugar. And we'll benzo protect it. So now we don't normally think about this because it's just something we haven't been considering. We talk about protecting groups, talk about protecting groups, and we're not talking about protecting groups for that ring thing. But of course, we know that this is in equilibrium with that. So it's a fast equilibrium. It lies mostly towards the ring, very little towards the open chain, but that is an equilibrium. And it's an alpha beta mixture. Now, there's not a chance in hell that you're going to be able to really trap this OH with anything meaningful. If you try and react to something that's going to react with an OH, it's going to react with this guy because this guy there's a lot more of that. So if you add in an acetate, like acetic anhydride, going, oh, you know what I'll do is I'm going to trap this as an acetate. You're not. You're going to acetylate your anomeric position because there's just so much of that. But you can trap the aldehyde. And so a common way of doing this.
So we make amines?
Yeah, you can make amine. You can actually make an amine there, but that won't get you the azo sugar. That will get you an exonitrogen. Because that oxygen, if you swapped it out for a nitrogen, that nitrogen will be out here. It won't be in the ring.
Okay.
So what you can do is you can take a disulfide and acid. You can actually do Wittig chemistry on this. Like you can actually use that aldehyde and do Wittig reactions and like make double bond carbon things and stuff. And we will talk a little bit about that when we talk about C glycosides. Not a lot, because I think we're going to just do one I think we have 3 more lectures on sugars. One on, maybe 4. One on this thing I wanted to do today, which was like problem solving on making glycosides, and I really want to do that before the exam. So I'm gonna put an announcement up, make sure everyone's here for Thursday. I think just everyone's tired. One on some C glycosides and carbo sugars, because I like C glycosides and carbo sugars. One on glycosidases and glycosyl transferases and the role of those enzymes and how they work, which will then transfer us into talking about peptides and amino acids. And then there's going to be one that's actually tacked on at the end of the course, where we start integrating glycopeptides and constructs where we incorporate sugars and amino acids and all sorts of other pieces in there, and really think about the materials part of the biomaterials, which is in the course title. We'll do some of that. So anyways, if we trap this aldehyde, it's an acetal formation, except it's with sulfur. And that's because those tend to be a little bit more stable than the acetals. The acetals are always in equilibrium. And the problem, of course, is your acetal would be in equilibrium with the hemiacetal of the sugar. And it's not super favorable one way or the other. The sulfur thingy, though, that there you're sticking. You're really sticking. You're making one thing. So you can trap that like that. Okay. Then we have some ways to turn that OH into a nitrogen. You're going to, like, if we want to have the nitrogen of the same thing, you're going to need to do a double inversion, because you're going to need to do one SN2, which will invert the stereochemistry of that position, and another SN2 to return it. And so actually a good way to do that is a Gary iodination, because that is an SN2. So if you remember what that was iodine, triphenylphosphine, and I'm blanking, and I think it's just iodine and triphenylphosphine. And that is going to give us for keeping track of our stereochemistry there. We've inverted the stereochemistry. And then we can take that and treat that with sodium azide. And we can get the stereochemistry. And of course, it's going to attack the iodide. And then we can get our stereochemistry back. We can get our azide back. Nothing happens to anything else on the molecule. It's a wonderful thing about benzoyl protecting groups. If you don't want something else to happen to your molecule, use benzoyl protecting groups. They are boring, and nothing touches them except like hydrogen gas and ozone. And then what you do is you just reduce. So you can do 2 reductions. Here what you actually might want to do is like be very clever and take off the sulfur and the nitrogen all at the same time. If you want to cleave sulfur from things, you use mercury is really good. But the other thing you can use is something called rainy nickel. It's named after an Indian chemist. And it's like porous nickel full of hydrogen gas, and other impurities. And it's weird. So I'm not going to try and pretend I know what rainy nickel is, really, because I think you never see it really described. It's just nickel. Anyways, it's basically like palladium on carbon, except it also breaks down sulfur carbon bonds and replaces them with oxygen. So this would create NH2 because it would burn down your azide. It actually would probably burn off all your benzyl groups too, depending. If you did it cold, you might be fine. Let's leave them on for now. You'd have to check to see. You might get unlucky or lucky. Actually, you will always get unlucky. If you wanted them to come off, they would not come off. And if you did not want them to come off, they would come off because fuck you, that's why. So what we'll end up here with is a nitrogen at the C5 position. So again, all we've done here is exactly how you think about this. You want to replace the C5 oxygen with a nitrogen. You protect everything else. You free up that OH, including this aldehyde. You protect that. You free up that OH. You want the same stereochemistry, and you want nitrogen there. And now you can't take advantage of that whole equatorial thing, even though it seems promising because it's not a ring. So you don't get that. You can't really trust that reductive amination to go the way you want it to. You're probably going to get a mixture because it's acyclic. So if you want the same stereochemistry you've got, you need to do two SN2s, one after the other. So displace it with one. I chose agarigoulination. You could have picked something else. Doesn't matter. You can choose whatever you like. You could do a Mitsunobu reaction. Love the Mitsunobu reaction. Whatever floats your boat. Then we do a second SN2 to restore the right stereochemistry with a nitrogen in place now. Again, notice that we're using azides for this because, again, azides are really well behaved. We could have used ammonia. I'd give you the marks if you did ammonia. But if you came to me in the lab and said you wanted to use ammonia for this, I'd say don't do that. It's stupid. Use azide. So we stick the azide in. We knock everything down. And then we just rig close onto it. And we go up to our azo sugar up there at the top. Because it spontaneously ring closes. Because six-membered rings like forming six-membered rings. I don't think I really have anything else to say about azo sugars. The cool thing about them is suddenly you can add R groups to the nitrogen there. So you can take it from a, like, it's not deprotonated. So normally, again, this is me without putting on my hydrogens. I'm really sorry. You can put, I'm sure I've done it somewhere else here. No, I'm good because there's just not many nitrogens in the rest of my molecule on this page. But you can put in like an R group on there. And so you see this in some of these antibiotics. And so you're seeing a lot of azo sugars as antibiotics because this bond here is going to be more stable to glycosidase. This is when we're going to talk about why that is. But maybe there's a pocket in the enzyme back in here that a normal sugar can't fill. But in azo sugar, you stick a side chain on here, suddenly it fits into this pocket. And now suddenly you have an extra hydrophobic interaction. And that's going to improve your affinity for the enzyme compared to the native sugar. So azo sugars are really, really useful glycosidase inhibitors. And they can also mess with making cell walls and stuff in bacteria. And so you do see them as antibiotics. But I just don't do a lot with them, so I'm just not as excited about azo sugars as I am about C-glycosides and carbosugars. Okay, I'm going to leave it there because we're at 5:22 p.m. We've gone for about an hour and 20 minutes. Thursday, we're going to just basically talk about strategies and ways to think about putting protecting groups together. And I just want to work through examples. Hopefully get through like 4 or 5 or 6 examples. And I want to try and do this as a group so that we're all kind of thinking about how to keep an eye on protecting groups and where we can move them. And it's kind of a puzzle. I find it really fun, but I'm sick in the head, so that's why I'm doing this for a living. Then again, so are 2 of you. Okay, I'm going to leave it there. I will see you on Thursday.
John, can I have a minute, please?
Yes, you can, Samara.
Yeah,
Is
thanks.
it course related or not course related?
It's course related. I just wanted to remind you about the lecture 9 not being on the YouTube.
Oh, shit. I will make sure
Yeah.
lecture 9 goes on YouTube. That is a really good point, Samara.
Yeah, I just want to remind you because I was updating the videos and they're,
It's not there.
It's just not there. I was actually cleaning up the playlist. So
You're wonderful. Yeah. Thank you for doing that. I will definitely do that. That is completely fair. I really hope I've got it. I'm sure I do. Okay.